All right, let's pick up where the last video cut me off. I'm almost done. So now we just had figured out that KSP is equal to x squared. So now remember it says the solubility product is 1.8 times 10 to the negative 10. So they're giving us KSP. So that's what we're plugging in for here. So let's plug into that. 1.8 times 10 to the negative 10 is equal to x squared. We're looking for the solubility in this problem, so we're looking for x. So we need to take the square root of both sides. And that's going to help us, or that will allow us to solve for x, which is the molar solubility. In this example here, when you take the square root of that, you get your x equal to 1.3 times 10 to the negative 5 molar. Let's look at one more example. This will be example 2 in your notes. All right, this example says 16th century physicians used calomel Hg2Cl2 as a medication. Their patients did not usually die from mercury poisoning. That's good. Because calomel is a sparingly soluble compound, so it does not dissociate to a great degree. Calculate the molar solubility of calomel, and they gave you the KSP. So again, it's wanting us to find the X, what we define as our shift in our equilibrium tables when we ice our problems. Again, first thing we got to do is dissociate our slightly soluble solid. So Hg2Cl2. You have to be careful on this one, class, because this is the mercury 1 ion. The reason I know that is because chloride will always cross a 1 down, and here it looks like it crossed a 2. Mercury 1 is actually a polyatomic ion, and the formula for mercury 1 is Hg2 with a +2 charge. This is the mercury 1 ion, and chloride is Cl-1. Now, there's 2 mercuries here and here, so that's good, but there's 2 chlorines here, so we got to put a 2 there. So again, make sure you balance your equations. That can be a sticking point on this one. All right, let's ice our problem. ICE. And for this, the solids are not going to affect the equilibrium, so we put no values there. In your initial row here, the zeros for the initial concentration of the ions, but once they start to dissociate, you define your shift in terms of x. So this will be a plus x here, and this will be a plus 2x here. So that means at equilibrium, the concentration of the mercury 1 ion is equal to x, and the concentration of the chloride ion is going to be equal to 2 times x. Okay, let's write our law of mass action or equilibrium expression according to this equation. So according to this, KSP is equal to Hg2 plus 2, and that's to the first power because that's the 1 there. And that's going to be times the chloride ion squared because there's a 2 here. So now let's substitute our values in. The mercury ion concentration is represented by x and the chloride by 2x. So KSP is equal to x to the first times 2x squared. Let's simplify this. KSP equals x times 4x squared, and KSP is equal to 4x cubed. Now that we have this in its simplest form, we can substitute in. We were told the KSP value in the problem. That plugs in here. So 1.1 times 10 to the negative 18 equals 4x cubed. Solve for x. Again, we're solving for molar solubility. First thing is divide both sides by 4. That's going to give me 2.8 times 10 to the negative 19 equals x cubed. Take the cubed root of both sides. And so when you do that, you get your x value. equals 6.5 times 10 to the negative 7 moles. And that's molar solubility. We'll work on some more of these in class tomorrow as we finish up chapter 17.